Hi everyone and welcome to the System Design POW. On this channel we do deep dives on various system design topics, and today we'll discuss the matrix aggregation system with different storage implementations based on the LSM tree and its scalability. How can we scale the data ingesters, queriers, compactors, and garbage collection? We're going to start with the high-level design and talk about the main components and design assumptions. As you can see on this diagram, we have 5 main components. Our ingester system is responsible for consuming and ingesting data from the outside. We have a querier system whose single purpose is to query our data stores sufficiently and return the response to the client. 2 middle objects represent our core storage system. Metadata storage would be a SQL database that maintains all the information about the files and chunks in our system. And object storage would be responsible for storing the raw data files in our system. Then we have 2 big support components. The compactor, which is responsible for maintaining and organizing our data on storage, and garbage collection, which is responsible for cleaning up the data that was removed and is no longer needed. As you can see, this design, all main components work independently with our data stores and do not overlap in their functionalities. They are completely isolated and don't know anything about each other, making it easier for us to scale them independently. For instance, if we have a lot of data and it doesn't get queried often, we can scale the ingester system independently from the querier and satisfy the requirements. But since every single component works with our storage independently, another assumption they're going to make is that we have a scalable SQL database for the metadata and scalable object storage for storing raw files. So we are not going to talk about how to build these 2 systems. We're just going to assume that they exist and they are performing good enough to withstand the load from our components. So the high-level workflow in the system would look like this. The data would arrive to our ingester system, which would consist of the ingest router, which would be responsible for partitioning all the data across multiple ingesters. The ingesters instances have to be scalable elastically and be able to keep up with the load coming from the ingest router. Once the time series data is consumed, we would store its metadata in our catalog and then the 5 objects with actual data points in the object storage. Later on, we would be using a compactor to compact many small files stored by the ingesters into our data storage. If we have retention of the data, then we would be using our garbage collector to identify data that has to be deleted and asynchronously deleted from both object storage and metadata storage. As they've gone through the right path, we know that the data would be kept in the object storage. We would have some metadata in the catalog, and we would also have some data in the ingesters because they would be consuming and collecting some of the data in memory. So if we talk about the query, then to fulfill the query, we need to look at 3 different places. First, check the metadata storage to understand the locations of the files we need to scan. Then we would need to read data from the data files, and then the result of it would need to be nursed with the data that we received from the ingesters, because every single ingester would have some data in the memory that is not flashed to the object storage yet. The querier would query 3D data sources, and then the result would be returned to the user. This is the fallible workflow of the system that we are going to talk about today. Now let's get into more details. Since we are designing a time series database, we assume that there will be a lot of writes, and the system has to be write-heavy first and read-heavy second. As we are consuming all these time series data from different sources, we need to make sure that our system is scalable and can keep up with the workload. We are going to partition the data horizontally because this is the only way to make the system scalable. So let's start with the ingesters and see how we can scale it. As the data comes in, we need to add a set of services that partition the data. In our case, if we use, for instance, a Kafka queue and partition the data on the queue, the ingesters would act as queue consumers. So as the data comes in to our API service, we would have a pool of API servers that would receive the data and send it to a centralized queue. Or it can be also a partitioned queue based on the different parameters. In our case, let's say we have a single queue where all the API servers would send the data. The queue would then be partitioned and have multiple partitions. If we talk about Kafka use case, for instance, it allows us to create as many partitions as we want. So in our case, let's say the queue has 100 partitions. As we have the setup done and we don't have a lot of data coming to our system, we can just have a single ingest node that consumes data from all 100 partitions of our Kafka queue. However, if the load increases and we need more ingesters, we can simply add more instances. More instances would consume data from Kafka faster and be able to parallelize the work of ingesting data. Let's say we have a lot of data, we have only 100 ingesters. We would have one ingester per single Kafka partition and then consume data in parallel. So as you can see on this diagram on the left, we have a single node. In our case, consumes data from hundreds of partitions and then handles all the work required to be able to store the data in our storage system. As they scale, we can either add more instances of the ingest nodes, or we can have ingest clusters that would be similar to having a multiple consuming group of the Kafka queue with multiple consumers inside the group. For instance, we can have a consumer group called cluster number 2 with 4 different consumers. This is a relative mapping of this high-level design to the implementation. Then every single ingest node would process data, prepare for storage, and then store it in our object storage and metadata storage. Now let's go through the detailed workflow. We are receiving the data in either the JSON format or the line protocol or any other data format. We parse the data and verify its accuracy, so we would likely demonstrate the time series against the metadata that we have in our storage to make sure that the data format is correct. Or we can use an actual data points to dynamically create a schema in our database if it doesn't exist. As we verify that the data is accurate, we would want to store it first in the write-ahead log. So every single ingest node has access to the disk and store whatever data is consumed in our write-ahead log. So in case the ingester goes down, we can read the memory state based on the data in the WAL file. This means that as data comes in, it's stored in multiple places. First, it's stored in memory and then in the WAL file. But the data stored in memory gets deduplicated first. We might be receiving duplicates from different devices that send us metric, so we need to deduplicate the data and also sort it in memory. We are going to sort the data based on the timestamp because in the end of the day, we want to partition all the data by the time. Every single file has a start date and end date, and the specific time frame must contain all the metrics inside the file. That's why when we sort the data in memory, we first sort it by the metric name or metric key, and then by the timestamp. This way, we have structured data from the time series perspective. At the same time, we can use the metric key and the timestamp to remove the duplicates. As the data comes in, we would keep storing it in the WAL files and the RAM memory. Then, either based on the size of the data in memory or the time frame, we would take all this data and dump it into our object storage, and then update the metadata about newly created file in the object storage. This system design is very similar to what Cassandra does. The only difference here is that we use time as a sorting key, and our files in memory and object storage are sorted and bounded by time. As a result, we have many small sorted files for the specific time frame stored in our object storage. In this state, it's impossible for us to clear data as the number of files would grow immensely, and we would have millions of files in the object storage that would be unusable. Instead, we are going to start compacting those small files into bigger files with the same approach. We would keep the data inside sorted. As you can see on this diagram, we have 2 files that need to be merged because the time frames on the data inside of the files overlap. We want to make sure that we have the data sorted and deduplicated. So the first thing we need to do is scan all those files and understand which files overlap. Then we collect all these files that overlap in the same time frame and merge them into a single bigger file. First, we would need to delete the data that is a tombstone or some delete operations that came from the ingesters. We scan for the data deletion and apply those changes. And then we need to deduplicate and merge. which means we would just need to take these two files of sorted data and make them a single file. Then we would encode, re-index, and store it back to the object storage. Now let's look at the example. Let's say it's been 10 minutes and our ingester has generated, let's say, 100 different files. As those files are generated, the compactor's job is to keep scanning for metadata of the newly added files, understand which files have overlapping timestamps, and merge files that have overlapping timestamps. So at the end of the day, for instance, if we have 1 hour time period, we can have 6 10-minute sorted files with data that doesn't overlap. This approach allows us to do efficient querying because we always know what file we need to look at to retrieve specific metric. In this diagram, you can see a visual representation of what happens with those small files as time goes on. So at the top, you see a lot of, let's say, level 0 files. Small files that come into the object storage, and in object storage we have partitioning, which is based on time. For instance, a 1 can be a 10-minute period or, let's say, 1 hour period. As the files that overlap with the 1 hour period come into the system, we would need to get those files, merge them together, and then, in the end of the day, merge them into a bigger file, which would be called an L1 file, which is responsible for maintaining all the data between time A and time B. All the data would be separated and put in a specific time range file. Now, speaking about the querying, let's say we have all this data process implemented. We have ingesters and compactors, and they work in organizing the data inside the memory of the ingesters, and also inside the object storage and metadata. How would clearing data work? It would work similarly to how ingesters work. We need to make sure that clearing is scalable and can scale up to the demand. So in our case, we would have a similar approach, as you can see on this diagram, where we can have multiple clearing nodes, and then we can organize these nodes into a cluster of nodes that would be responsible for serving specific use cases. For instance, one cluster can be for the internal use and one cluster for sales, etc. Scaling would work by using caching extensively, because we know that if specific data was queried once, it's likely going to be queried the second time and the third time, and so on. Whatever data we return to the query, we would want to cache locally. At the same time, every querier would need to maintain an up-to-date state with the metadata database, which means it has to have a separate copy of the index that knows where to go for specific timeframes, metrics, and data. This way, this index can be used for the specific use case. For instance, if this is an internal use of the database, then we would likely be indexing more internal metrics of the services, such as CPU, RAM, etc. If we have a separate create a cluster for sales, we would cache different set of metrics, such as response time, purchase amount, etc. Every query cluster has its own state but caches the most recently queried data. Now the question is, how are we going to query the data? Because we have multiple sources, right? We have the data stored in the ingesters. We have the data stored in the actual object storage. So we would need to get all this data at the same time concurrently. As the query comes, first we need to generate a query plan for what files we need to be queried and what data has to be retrieved. Then we would execute it concurrently, which means we would send requests to get data from the ingesters within a specific time period. Then we send requests to the object storage. If we don't have data about the locations of the metrics, we would first query the metadata database to retrieve the locations of the files, and then query the actual object storage to retrieve the data. All these results would then be aggregated and returned to the customer. Before returning, they would be cached. The query fulfillment would be very efficient because first we need to read data from the ingesters and the data stored in memory, so it would be fast. Secondly, if our cache and index are up to date, we wouldn't really need to query the metadata database. We would be able to go directly to the object storage and retrieve the time frame that we are interested in, and then the specific metrics inside the files that are responsible for that time frame. Okay, in this video we've covered the high-level design of every component of the metric aggregation system. If you find it useful, make sure you like and subscribe, and I'll see you in the next video. Bye.